Hey guys, welcome to the Mind and Machine lectures. We're going to talk about how we integrate cognition with neural networks or machine computer networks. So, this all got its start in the 1950s. Computers were really kind of taking off, they started becoming a thing, and we started thinking about the mind as an information processing machine. And using this analogy of computer to mind allowed for a conceptualization as well as implementation option of of how we take in information, how we use information, how we store information, how we retrieve information, right? So it really gave us this avenue for modeling neural activity. We could ask how information is being handled by our neural networks with neural networks, machine neural networks, right? So, how is the calculating being done that we talked about with the neurons before? How do we quantifiably represent inhibition, excitation, thresholds, etc.? And a great way to do that is with algorithms. Okay, and computers are really centered around algorithms. And an algorithm is a set of rules or instructions. And the purpose of an algorithm is really to govern or execute a function. Now, they have been around forever. Okay, this picture on the screen here is an ancient Babylonian tablet. So the Babylonians came up with factorization and finding square roots. The Egyptians before them had an algorithm for multiplying two numbers. Okay, so we've sort of had this idea that, hey, we can set up a rule, a method for dealing with these kinds of problems, and we can just use this rule all the time. Another big algorithm, Euclid's algorithm, okay, right, finds the greatest common denominator of two numbers. So, for example, what is the greatest common denominator of 56 and 12? First step, divide the larger number by the smaller number. Okay, so that's 56 by 12 is 4. You have a remainder of 8. Now you divide the divisor, right? You divide the divisor of the previous step by the remainder. So now you have 12 divided by 8 equals 1 with a remainder of 4. You keep doing this until you no longer have a remainder. In this case, it's pretty easy. You only have to do it one more time, right? So you take the divisor, 8, and we're going to divide it by 4. There's no remainder, so GCD is the last divisor, right? So the greatest common denominator for 56 and 12 is 4. This is just an illustration of how this concept works, and I'll let you have a look at that illustration and sort of piece it together. It took me a minute, but once you get it, it makes sense, and the visual analogy is pretty cool. Okay, so when we think about modeling the mind with the machine, we have to ask certain questions. And the first question that we want to ask is, what can a neuron do? Okay, so we need to be able to set up our model to do what it is that we need it to do. Like the actual model unit has to have the same function as a neuron, right? So what can a neuron do? Well, William James, back in 1890, before we even really knew the inner workings of the neuron and how they worked, he wrote Psychology, the briefer course. He's actually considered the father of American psychology. There's him looking all cool. This picture apparently was taken in Brazil when he was a bit younger. I just thought he looked very like hipster chic. I don't know. Things are a little baggy. Anyway, whatever. There's Mr. Dr. James. He came up with Psychology, the briefer course. He was the first to teach psychology in America. He was the first to come up with a real psychology text that's over 100 years old. This is it here. And so, right, so he really has contributed to this study of the mind and how the mind works. And he speculated before we knew anything about any of this that the amount of activity at any given point in the cortex is the sum of all the other points to discharge it. Now think about that. Think about what the quote means. It essentially encapsulates it encapsulates the neural processes, and this is before we knew anything about them, right? So he really had this grasp, this understanding of what was going on before we did as a field. Okay, so what does this mean in practice? Okay, what does it mean that the amount of activity at any given point is the sum of all the other points to discharge it? Let's talk about it. So first we need to talk about like what a neuron can do in terms of in real life, right? Biologically, we've talked about this neuron is it's maintaining a membrane potential, right? It reaches a threshold and then it fires, it has an action potential. So it's computing information to get to a threshold, right? So it's using a threshold function. And the threshold function involves information of a spatial and temporal nature, okay? And the idea is that we have to integrate the spatial and the temporal. So if you think about a neuron, this is my handy dandy little model here. You think about the fact that neurons, they are being synapsed upon by other neurons, right? So the dendrites of one neuron, of this neuron, these dendrites are connecting to other things, right? So this neuron is taking into account what things it's connecting to and where. And it's also taking into account what things it's connecting to over time. Okay? So let's explain a little better. So these are our dendrites, right? X1, X2, X3. You can have an unlimited sort of number of dendrites. There's not a cap on the number of dendrites you can have. So, silence the watch again. Sorry, guys. Okay. So these are all our dendrites. This is all the input that we're receiving from the environment around this neuron. And we can say that we have neurotransmitter input to the nth dendrite, right? So we have n amount of dendrites, right? So we have x to the n neurotransmitter inputs. All right. Now, when we have input, the body of the cell is summing that input over time. So essentially what this is saying is I want to take the sum of every instance of neurotransmitter input over time. Okay? So a couple guys named McCulloch and Pitts decided to put some of the ideas behind information processing in a neuron to work in a model. So here is the McCulloch and Pitts simple neuron. Okay, you can tell this is equivalent to a cell body. Here's some dendrites as inputs, right? Here's your axon and output. Okay. They wrote a paper called A Logical Calculus of the Ideas Immanent in Nervous Activity. Now, this paper made a few assumptions about neural activity in order for this modeling process to work. Okay, the first assumption was this: a neuron has binary inputs. Okay, so what they're saying is that A and B, let me just get my pen situated here. So A and B can either be 0 or 1. 0 or 1. Okay, so there's our first notation. Now we know that this is not true, okay? We know that we have graded potentials. We know that we can have varying changes in membrane voltage differences. We know that small stimuli can cause small amounts of depolarization. Larger ones can cause larger changes, okay? So that's the first assumption that they have to make with this model. And the second assumption is that excitatory inputs are going to add linearly and inhibitory inputs are going to prevent firing. Now, we also know that that's not true from graded potentials. They tell us very differently. The third, a neuron has a fixed threshold. Okay, well, we know that neural thresholds are not fixed. They change over time. So if you think of something like neural adaptation. So for example, you walk into a room, it smells horrible, but for whatever reason you have to stay in that room. 10 minutes later, you're not as bothered by it. Honestly, it's not like it doesn't smell as gross to you. And the reason why is because you've adapted to that smell, and it would take more of that smell, like a greater saturation of that smell, for you to be as grossed out from that smell as you were when you initially walked into the room. Why? Your threshold has been raised. So when you raise the bar, you need more of it in order to be as disgusted by it as you were. Same kind of thing with something like drug use. You need more drugs in order to achieve the same amount of satisfaction from them as when you started using the drug in the first place. Okay, so this is the fixed threshold here, right? The theta is our threshold. So in this case, theta is going to equal 1. Now, they also say that a neuron has binary output. Now, we know that that's not true. It's not 1 or 0 all the time. We know that output gets a lot stronger when you repeatedly stimulate a neuron. We know that it's not an on-off switch. It's more like a dimmer. But okay, for the sake of their model, your output is either going to be 0 or 1. Okay, so let's talk about this situation. I have a threshold here of 1 in my first situation. If I have a threshold of 1, that means that either A or B, so A or B, I don't know why B is capital and A is not, so we'll just, so that A doesn't get jealous. Okay, this is an A or B situation, right? So if A is 1 or B is 1, then theta has been met and we will get 1, right? Okay, now, what happens if we change theta? What happens if we change theta to, actually, let's do this so we don't get confused, right? A or B situation. Now, let's say that theta is 1.5. What happens now? Now we need but we haven't met the threshold yet. We need A and B in order to meet our 1.5 threshold in order to get our 1, right? So now we've made it an and function. So what is my point of illustrating this to you? And my point is, I'll get there, that when this sort of situation is built upon, you can get a combination of a whole lot of logical propositions. Very complex networks can realize any finite logical expression. Finite meaning there's an end, there's a solution, there's an output, an end to it, right? So you can get a network to realize any combinations of if this, then that, or this, but this, and this with this, and all the things, right? So you can get all of these propositions into a network using these principles and these assumptions. So at the time, this didn't actually have much of an effect in neuroscience literature. I don't think it was realized right away by the neuroscience folk how cool this was for neuroscience as a field. The computer science people were like, whoa. Binary operations, logic gates, computation, etc. We can do a lot with this. Okay, so they really, really recognized it. It was easy for them to see the connection between the McCulloch and Pitts neuron model and the work that was going on at the time, which was it had a lot. There were a lot of binary operation things going on. Now, this is the father of computer science, and this is what he wrote in a 1945 technical report. It's worth mentioning that the neurons of the higher animals are really like elements. They have an all or none character, that is, two states, quiescent and excited. An excited neuron emits the standard stimulus along many lines, axons. Such as a line can, however, be connected in two different ways to the next neuron. First, in an excitatory synapses, so that the stimulus causes excitation of that neuron. Second, in an inhibitory synapses, so that stimulus absolutely prevents the excitation of that neuron by any stimulus. Following Pitts and McCulloch, we ignore the more complicated aspects of neuron functioning, thresholds, temporal summation, relative inhibition, etc. It can easily be seen that these simplified neural functions can be imitated by telegraph relays or by vacuum tubes. Okay, so he's saying, yes, we're not encompassing all of the mechanical aspects of neural processing, but we're encompassing some really important ones, and those are ones that we are really interested right now for what it is that we're doing. And what they were doing at the time was this was all about code cracking. Okay, this is in the middle of World War II, or at the start of World War II. The Germans are sending complex codes using a machine they called the Enigma machine. And Turing, Edward Turing? Have I forgotten his first name? Well, Turing and his friends were trying to crack the codes so they could win the war. And a lot of what they were using for code cracking were things like binary computations, if-then statements, if-then and or statements, in order to crack these codes. Check out the movie The Imitation Game if you haven't seen it. It is, it's a very Hollywood tinged sort of context, as they do in Hollywood, but it's a pretty cool movie. And it tells you a little bit about the feel for computation at that time. Oops. Okay. That's all, folks, for what a neuron can do. Next, we will talk about what a neuron can know, and I will see you there.